Hello there. So this set of slides is going to mark a pretty good transition for us in this course. We're going to shift away from a lot of the stuff we've been talking before. We won't see many divide and conquer algorithms again. We won't see a lot of iterative style algorithms. We won't see a lot of randomized algorithms. Those topics will continue to come back up, and so will asymptotic complexity and a few other things we've already talked about. But a lot of the remaining part of this course will be focused on graphs. So this set of slides is just to remind you some of the basic important aspects of graphs that you may have seen in your data structures course. All right, so really graphs just can be boiled down to this. They represent pairwise relationships. So for example, they just have a ton of uses. You could think of them as representing in code physical connections, so roads, and then the problem you're trying to solve is giving driving directions. They could be the physical connections of a network. So the phone system, how do you route one phone call request from one location to another? A lot of these things are automated already, but there was a time when, for example, network routing wasn't automated, and a lot of these graph algorithms would have had to be done by hand. They also represent relationship groups, so social networks. If you've purchased something on Amazon and somebody else has purchased that same thing, usually Amazon will create a graph where you and this other person are related, and now when they buy something new, you might get that as an advertisement. They're also used pretty heavily in problem solving. So, for example, in Sudoku or chess, you can have each instance of the game board as a node in a graph. So taking chess as the example, you could have your initial starting board and then all adjacent nodes to that, so that is all nodes that are connected to that starting node, are all single chess piece moves that you can do from there. And what you're trying to do is find the most efficient path from that starting board node into a node that denotes that you've won the game. And there are a bunch of algorithms for graphs, so cuts, clustering, searching, partitioning, contracting, and we'll be covering quite a bit of those. And just because I want to really emphasize how important graphs are, I don't want to make you think that it's just those are the only use cases. They're also used in signal traces on a PCB, balancing the load on a server, balancing the loads across cores on a computer, and so on. So the list just will continue to go on and on sort of what graphs are useful for. And if that doesn't really have you convinced, then maybe just take this part to heart. Because they have so many use cases, they're going to be very frequently embedded into questions you get in interviews. All right, well, let's start with something that's kind of fun and really easy to see. So what we have here is a maze, and we're going to look at a few different algorithms for getting from location A down here to location B. So we're going to look at Dijkstra's, an algorithm called A-star, breadth first search, and depth first search. And the way you would read this graph is that anytime you have two cells that are adjacent to each other, they have a connection. So normally we would denote that like this, and maybe you can go in both directions, so I won't draw an arrow. If I could only go in one direction, I might draw an arrow there. But that's what this grid cell is denoting, is sort of the connections between graph nodes. And the darker a shell, so this one's shaded gray, that means it's more costly to move into that one. If you're here, it's cheaper to move into that one. And really more importantly, if you're in this cell, it's cheaper to go down than it is to go right. So that's what the colors are going to denote. So this will be an animation, and as you watch this animation, there are a few things to keep an eye on. Operations is sort of related to how this algorithm actually works. How many different cells is it going to look at? Unexplored is how many cells do we leave unexplored, and we would really want to maximize that, right? We don't want to explore every single vertex just to get from the upper left to the bottom right. Open, or how many pathways do we have open currently? So here to start with, we only have one pathway open. We can only go to the right, and then we can only go down. We can only go to the right. We can only go down. And then from here, we have two pathways open. We could go to the right, or we could go down again. Closed, or how many times we've hit a dead end. So for example, if we come all the way down to here, maybe we're at this cell, we can no longer go that way, so we have to start backtracking, and we would call that a closed path. Path length is going to be the number of vertices or nodes that we visit. So 1, 2, 3, 4, 5, 6, and then cost is going to be the weighted cost of that path length. So some of these paths will be cheaper than others because some of them go through only these lighter color, lighter shaded cells. Alright, well now there's nothing left to do but sort of show you this animation. So this is Dijkstra's algorithm, and this is an algorithm for finding the shortest path from a start vertex, that would be A, to every other vertex, and B would be included in that every other vertex. So there's the shortest path. Before we move on to the next one, I should note here that you'll notice that there is no cheaper cost than this. Dijkstra's is guaranteed to find the cheapest cost path. A star is sort of a variation on Dijkstra's where you give it a little bit more information. So we would expect it to come up with the same shortest path, but maybe do a little less work to do that. So by that I mean take a look at the operations column when you're comparing two things that get the same total cost. Alright, let me skip forward here and let A star refinish up, and then I'll just let depth first and breadth first and depth first finish up without interrupting. Alright, so those are 4 different algorithms for solving this problem, and as you might see, they don't all end up with the same solution. So Dijkstra's algorithm and A star are guaranteed to find this cheapest cost of 65, and they ended up finding the exact same path. Breadth first search didn't find that optimal path, so it found something that was shorter, so it had a path length of 51, but the cost of that path was longer. Dijkstra's, depth first search, didn't have anything sort of desirable about that, except maybe it left a lot of cells unexplored, and it did the fewest number of operations. So each of these algorithms are going to have their own sort of characteristics and advantages, and we'll talk about why you might want to use one versus another as we go on throughout the next few sets of slides. The last thing I'll mention here is just comparing BFS, Dijkstra's, and A star, since those sort of got pretty close on the final result here. They're very similar to each other. Breadth first search is always going to, for example, start here in the middle. It's always going to explore the graph in shells. It's always going to go out by the same amount every time it goes out in shells. So it's going to look at everything that's 1 hop away from the start vertex, 2 hops away, 3 hops away, 4 hops away. Dijkstra's algorithm is pretty similar, except for it actually takes into account the edge weight. So how much of a cost is it to go from one vertex to another? So maybe it's really costly to go this way, so we don't make as much progress there. And maybe it's really cheap to go this way, so we make a lot more progress that way. And then A star is a lot like Dijkstra's, except for we kind of cheat and we tell it something about where the goal location is. So it's a more directed version of the search.